Okay, in continuation in the previous discussion that we had, we are continuing uh, in this part, which I think it is part 3 of this series uh, on the Kirchhoff-Love plate theory. We have discussed so far that we get the stresses for the plate theory related to this plate theory. And these stresses we calculated in terms of the W, the deflection in the Z direction. And we also identified that there is a kind of road that we have to be careful going along to get to the final results of this theory. We call it KL theory to have it in a kind of brief acronym name. So we started with geometry, then we identified the assumptions, and the most fundamental one is that the material line perpendicular to the midplane remains a line, and then also perpendicular to the deflected midplane. That gave us some kinematics, and then we use active rotations very effectively to get to our displacement rigorously. And then we got our strain. And the strain, if you recall, the strains are the shear strains are 0, as well as the strain in the Z direction is 0. And then we needed to take care of the strain to stress relationship using Hooke's law. If you use the 3-dimensional Hooke's law, we ran into an issue. We get a stress in the Z direction, which is a problem. Also, we get shear transverse shear in plane stresses as we saw in the stress, the 3-dimensional stress, these two, which is sigma xz and sigma yz are 0. These are problematic, but the most problem comes from the sigma z. So we had to do a kind of averaged 3D resulted in 2D elasticity. We call it plane stress with a quote unquote by integrating the 3D along the Z, and then we plugged in the strain, and then we are at this point. So we want to get the governing equation. So this is a quick background or quick review of what we have done so far. So now we would like to get to equilibrium equation. Once we have our stresses established, as we did here, these stresses should satisfy the equilibrium equation in order to get a constraint or a framework as for governing W, which is our only variable here, basically. Now, the equilibrium equation in 3D reads like this: sigma ij, comma j plus chi I equal to, could be a force, body force or something. Let's call it dp to 0. So this is body force. And these are the derivatives of stress. If you expand on this, you get something like this. And I will drop the indices for repeated indices here. And similarly for y. and I also use the symmetry here. So sigma yx is equal to sigma xy. And finally, for the z component, sorry, this should be yz sigma y plus sigma z equal to 0 equal to 0 equal to 0, and then here we take chi equal to 0, just for simplicity, without losing any generality. So to be clear, what we are talking about here is that if I kind of expand zoom in on a plate element in my xy coordinates, this is sigma x, this is sigma xy, maybe I write it such that I have room for the others. So this is sigma xy, this is sigma xz, and correspondingly on this side sigma y, sigma xy, and sigma yz. Obviously, on the other opposite sides, to this plane on the left side, we have the similar set, and on the back, opposite to the normal to the y-axis, we have a similar. Okay, so now if I have let's say a set of applied load here, for example, could be point load, could be distributed load, and obviously some set of boundary condition support, could be simply supported, could be clamp, could be anything on the boundary condition of this plate. These stresses that we calculated so far based on our kinematics and then kinetics using the averaged Hooke's law in two-dimensional should satisfy this equilibrium equation. This is the bet here. Now, we have already know that if I go back a bit further, although we are not going to use this one, but this explicitly says that sigma xz, sigma yz, and sigma zz, we discussed that extensively before, are 0. But this is the very important but. I put in this bracket here, note, we have sigma xz equal to sigma yz equal to sigma, well, maybe I put this now for these two separate because these are shear, and then sigma z equal to 0. So these two are shown here. So sigma xz and sigma yz. These two transverse shear. And sigma z, which is the normal, maybe I show this in a different color here. If you want to define sigma z is this stress. and obviously at the bottom. On this plane, we have some traction, so we need that. And on the bottom plate, usually on the bottom, there is no load applied, so this sigma z should be 0. So these are the things that we see immediately from the requirement of equilibrium equation, that we need to have some values with it. But at the same time, we see that our resulted stress tensor using the Kirchhoff-Love assumptions, it doesn't give any values to these stresses. So again, you see that we have some Apache road again here even as well. So what we will do is we will play the same trick that we played on the constitutive equations. We will integrate these equations and then use some quantities that represent these stresses. We call it intensities sometimes. These quantities are basically the integral of these entities, these stresses, and then using that we will get to the final answer that we have. I give you the final answer before going through, and maybe I go faster because it's maybe kind of a lengthy process to go. So the goal is, maybe I keep this. The goal is to get an equation which governs W, the deflection. And the answer is, I'm just giving you the answer, is by harmonic function acts here of W is equal to Q over D. So have this on the side. I'm not claiming that this is given, but this is the goal. This is what we will get to. So by harmonic equation is, if I want to write it again here, is d4w dx4 times plus 2 d4w dx2 dy2 plus d4w dy4 is equal to q over d. And q is simply this load that we have. And d is a parameter that I will define, is a constant that I will define. So this is what we are getting to. Now we are going to understand what is going on here by looking at the variation of stresses along Z, the depth. So if you go back to the stress and pick up the first one, sigma, this is sigma x. Obviously multiplied by this coefficient here. W is a function of x and y. So this whole thing is a function of x and y. And this is a constant E and mu, and Z. So therefore this sigma x is a function of x, y, and z. But it is a linear function of z because everything else becomes a coefficient to the z. So we can say that sigma x varies linearly along z. If you look at other stresses, sigma xy is the same because it multiplies by z. And similarly, sigma yy is the same. And here we can say that sigma x, sigma y varies linearly along z, and sigma xy varies linearly along z. Okay? Now, if we have that, then if I come here and maybe get one of them, let's draw one of them at least, or maybe all of them, but I explain in detail one of them. Let's say this sigma z. So this is my, let's say, x, z, and y, right? So this sigma z, sigma x, varies along z-axis. So if my coordinates is 0, so maybe I get rid of this here and then draw it accordingly. So here my z is minus h2, assuming that my thickness of the plate is h. So this is my origin. And here is z is h over 2. So therefore here it has some value at z equal to 0 should be 0, and then it will be varying linearly along the z. So if I want to sketch it, becomes like this, perpendicular to the surface. Similarly for sigma y and sigma xy, actually it is a torsional or twist. So I will draw it here on the same plane. So this will be in plane. So this is in plane. The same coordinates, x and y and z. So this is in plane, this is normal to the plane. So this is sigma xy. So you see here that you will have a twist or rotation due to these stresses, as if they want to twist the plate in the direction. Of course, on the other side we will have the balance of these stresses. But this will create bending. This create bending. This create torsion, or if you like, twist. And similarly for the side perpendicular to the y-axis. So I will come and give it these quantities a name. The bending, I call it mx. So mx is the bending. Bending. My is the bending. You can also specify the axis that they are bending. So if I have a bending here, because this is my x-axis, actually mx becomes the bending about y-axis, if you like, about y-axis. and this is about x-axis, and mxy is a twist, shall we say, about x-axis, because it wants to twist, it will create an in-plane moment about the x-axis, and similarly myx about y-axis. Okay, how about sigma z? Actually xz, the transverse shear that I identified here, this and this set, yz and xz, is shear in z direction and we designate it by an intensity, call it q. So these are the quantities. So basically, if you recall, in the beam theory, we did this with shear and bending moment and so on. In plates, we identify the quantities that these stresses are responsible for, because we have to integrate this. So basically, we are identifying quantities that we will use in the integration results of this equilibrium equation. But also it benefits us from understanding of what is actually going on here. I should emphasize here that the equilibrium of the plate element that we have here clearly tells us that the kinematic to kinetic assumptions, we have to make sure that the results satisfy this equilibrium equation, and therefore there is a need to consider one by one of these stresses on the sides of the plate. So if we say, let's say this, some of them are absent because of the calculation that we did, and then we take it, basically, if we go there, then this will be identically zero, and this will be identically zero, and then you will end up with this four terms, two terms here and two terms here. So basically, you are doing a two-dimensional stress equilibrium equation, and the result that you will get, you have totally ignored the shear effects on the side of the plane, although it is small, and I will discuss it at the end. But it is, the trick here is that we can, by order of magnitude, they are small, but we cannot ignore them because of the requirement that we have here for equilibrium. That's a very important point to understand in plate theories in general. Okay, so let's number these equation 1, 2, 3. Maybe I don't think I numbered any equation before, so we should be good. So 1, 2, 3. So when I say 1, I mean this one and so on. So this is the x component, y component, and z component of the equilibrium equation. And then I come and do some operation. The operation involves integrating equilibrium equation, I mean each component. Okay, so what we do, we multiply 1. When I say 1 here, I mean this equation, the first one here, multiply by 1 by z, and integrate from z equal to minus h over 2 to z plus h over 2 to the bottom surface, from the top surface to the bottom surface along the z direction, because remember our z is downward positive. So if you do that, then you will get, I will write few terms and then use the result to write the others. But if you pay attention here, for the mx is actually, if I write here, it is integral of sigma x times z dz, integration along the. So if you want the whole mx is basically integration of these stresses. So this is a area element times the sigma is the force, and then times the arm of that force, which is z along the z axis. Therefore you will get this is mx. And similarly for my is integral. I will skip the limits, is sigma y z dz, and I will talk about mxy. So here, if you look here, then this will become actually, this is an integral about the z. Sorry, this shouldn't be about the z, and then this will become dmx dx. Okay, because mx, as I wrote it, and I write it here, sigma x dz. Okay, and then for the next term, we multiply by z xy dy dz is dmxy dy, which mxy, as I explained for the mx, similarly is z sigma xy dz. This is basically the quantity that we discuss here. So if we want the moment of this stress, the torsional moment, then we have to do this integration. And then for the z, the last term is z dz dz dz. So here we can, because everything is differentiation by z, do by parts, and this will give us, integrate the, actually this is xz, so this is z sigma xz from minus h over 2 minus the integral part, which is sigma xz. Derivative of z is 1 dz. This term, if there is no traction on the top and bottom, sigma, there is no shear, shall we say, shear traction. Because if you look at here, and if I want to write it again here, this is sigma xz. I mentioned it somewhere here. Yeah, here. Sigma xz, and there is another one sigma xz for balance here, right? And similarly at the bottom. So these two should be equal for compatibility and complementary shear stresses. So this is, if there is no traction, that stress is zero. Therefore, usually we take this zero, unless you have specifically a traction there. But for plates, we usually consider it null. And then we are left with this quantity. We call this quantity Qx. So therefore, this is minus Qx. Now, therefore, I can say that if you sum up all of these things, according to the first equation here, if you sum up all of these expressions that we have here, summation, this will give me dmx dx plus dmxy dy minus qx equal to 0. So this is the result of summation of this, because from equilibrium we calculated each term and then sum it up equal to 0, and then we have this equation. Now, similarly, a similar operation for equation 2, or from equation 2, actually, I should say. We get dmy, or maybe I write it the order that we have there. Okay, dmy, that's good. dy plus dmxy dx minus qy equal to 0. Let's call this equation 5. Now, for the z component, always we have to be careful in this theory with the z component, which is this equation 3. We don't multiply it by z. Now, we integrate 3. No z multiplication. Because it's already in the z direction, so we use the intensity of that. So this becomes d sigma z dx dz, and all of the limits of the integral is minus h over 2 plus 2 plus h over 2. But what is this? This is actually qx. This is qy. And this is something that we can calculate by parts. And this will become sigma z the integral from minus h over 2 to plus h over 2 minus. Actually, we don't need by parts because this is already there. We don't need by parts. And this will become what? This will become sigma z at the top minus sigma z at the bottom. So at the top we have a traction which is minus q. At the bottom usually we don't have any applied load, so this is usually 0, and therefore we get our equation. But this minus q is in the, because our z is downward, so the unit normal is upward negative, so the minus q as a stress becomes a positive one. So therefore actually here this should be xz, so that is qx. If you go back here, we define qx as the integral of sigma xz, and then as I mentioned, this is q but minus q, but the direction of minus z, therefore it is plus q as a stress. So therefore here we will have qx dx plus qy dy plus q equal to 0. And this is our integration operation complete at this point, 4, 5, and 6. So what we have done so far, basically, instead of using the equilibrium equation directly, we did integration to bring in the quantities corresponding to the stresses on the sides of the plate, the planes which are perpendicular to the x and y direction, and also looked at the shear stresses in that way. Now, here we will do some more operation, and that is we come here and using this equation eliminate qx and qy from 4 to 6, and that is simply because we have the summation here, we bring this qx qy to the other side and sum it up, and then for the summation of these two we put minus q, and this gives us the equation in terms of m. Let's call it star, equation star, because we will refer to this again. Now we have to do some operation in order to put in terms of plug in terms of mx in terms of w. But when you go back and look at the mx is the integration of these stresses, right? So I will do one, and then similar operation can be done for the others, and then we are close to finding our final results. Okay, I wrote down this derivation here, and I explain it now to save some time. So what we want is this term here. So, but we know that mx is defined as this, as we defined it previously, mx. But sigma x, now I go back to my stress tensor that I calculated before here, and pick up my sigma x in terms of W and plug it in here. So when you come back, you have this z sigma x with the coefficient, and there is a z. If you go back here, so maybe I should also mention that the coefficient, we put it here. So this coefficient multiplied by this term is my sigma x, my whole sigma x. Therefore, I have another z here, and then dz, and this piece is sigma x. This is a constant, can come out. Actually, this can come out as well, because this is not a function of a bracket. The derivatives of w is a function of x and y, so the whole thing can come out of the integral, because integral is with reference to z variable, and so this comes out, and then you will end up with the integration, which is very simple. Between minus h2 and h2, this becomes h to power 3 divided by 12, and then you bring this here and you will get this result. So similarly, can say similarly, d2 my dy2 is equal to, let's call this quantity d, so I don't have to write it again, and this is very common. We define this. This is not a material property, a property of the cross-section shape. This is simply resulted from, as you see here, the integral of z squared dz along the depth. So having that, maybe I also include the e here. So this include e, and then I keep the minus for now. So this becomes minus d d2w dy squared plus mu d2w dx squared. Okay, and similarly for and also d2 mxy dx dy is equal to minus d sorry, a correction here. This is mx, and when I take the double derivative, this thing should be actually d4. So this becomes d4w dx4 d4 dx squared. Yeah, because I have to differentiate this twice with respect to x, and then I get this. And similarly for this one, This would be T4 and 4. Sorry. It's good now. And similarly for x, y, this becomes minus d, 1 minus mu, d4w, dx2 dy2. This term comes in because when you do the calculation, this comes in because of this term. So basically this becomes 1 divided by 1 plus mu, but we multiply it by 1 minus mu to get the same denominator, so we can maintain the d as we defined it by 1 minus mu square. Okay, so that's done basically. So plug into the star. The star equation is this guy, and then you get the celebrated results of d4w dx4 plus the mu, the terms related to or multiplied to the mu will cancel out nicely and beautifully. And q and d goes to the right. So maybe I double box it here. This is the, let's caption it with, this is the governing equation for deflection in Kirchhoff-Love, in a Kirchhoff-Love plate, I mean, according to their theory. As I mentioned here at the beginning of this part, this is also written as biharmonic, which is the Laplacian of Laplacian of W. So basically what we are saying here is that it's a fourth order partial differential equation. The Laplacian of Laplacian of W should satisfy this equation according to the applied load and some constant that we defined here, according to the material property and the H and mu. And that's, so I would like to end this quickly, end these things in order of magnitude. We kind of wrestle with the sigma x, sigma y, z. That it gave us 0. If you go back to the string, way back to the string, you know, these are 0. And then we had, we get the stress is 0 according to the kinematics and kinetics that we had. And now we kind of maneuver around it to get it back by some integration along the z direction, and we got to the beautiful biharmonic equation, which is so beautiful that we don't want to throw away. And actually, it works very well. But how well it actually works? So R smaller than sigma xy. These are shear stresses by order of h over l. So this is one. You can actually do this. I will not do it here, but it is an order of magnitude analysis that as your h over l gets smaller and smaller, these assumptions that we made here are more justifiable, as well as the result for your calculation using this theory becomes more accurate. Now, the sigma zz, which is another difficulty that we had, is smaller than sigma xx and sigma yy. Sometimes I write the repeated indices 1, sometimes I 2, by actually even better order of h2 over l2. So if hl is small, h2 over l2 is much smaller. So this guy will be justified to the treatment that we have. And recall that for this theory to be valid, we need to have HL less than approximately less than or equal to 1% of the in-plane, 10% of the in-plane dimension, right? So let's say if you have a plate of thickness of 3 centimeters, as I mentioned before, so if your plate dimension is about 30 centimeter plus, you are good to go. I hope these 3 videos help you to understand the plate, two-dimensional approximation of three-dimensional elasticity. And the first theory that we did here is Kirchhoff-Love plate theory. It is a simplified version of the overall behavior of a plate. It is very much similar to the Euler-Bernoulli beam theory by having this condition that we discussed. And throughout the journey, you saw how we had to maneuver around these assumptions, but keep this theory alive and useful as it is based on the condition that we discussed. Thank you very much. So I noticed a couple of typos that I had in the video, so I would like to correct it. And that is actually dy squared. So that is one correction that I wanted to mention. The other one is some of the indices in the equilibrium equation, although the answers are right. So let me write the full indices here. The first one is good. This should be xy. And this should be yz, and this should be xz here. Mx index x was missing, and the rest are good. So now it is good. So please note these minor correction. Another one is this integration that we had here. Just to be clear, so we are calculating here. Let me clear this maybe and rewrite it. To be more, the answer is correct, so it should be Q, but I wanted to explain why it is that. So this is, when I say top, I mean H at plus H2. Actually, it is bottom, and bottom is minus H2, H over 2. Okay, so let's clear this top and bottom. Okay, so this is actually at Z equal to H2 and Z equal to minus H2. So if you come here, okay, so because we have Z direction, this is the thickness, this is our origin, Z is downward, here is minus H over 2, here is H over 2 plus. So this is at H over 2, so this is at the bottom, the upper limit of the integral is at the bottom, and this is at the top surface. So here at the top we have some values actually. Sorry about that. And the top we have some values. So maybe I make it a little bit smaller so I can write it here. So here at the bottom we don't have usually attraction, but at the top we have. And what we have here at the top, the normal, because this is downward, the normal, positive normal is in this direction. Positive normal Z, shall we say, it is in this direction. And the stress, which is Q here, is downward. So it is minus minus. So this guy becomes minus minus Q, which is plus Q. That's what we used here, and that is correct. So these are minor corrections that I wanted to make. Thank you very much.